Today we are going to take a look at polar coordinates and polar graphing, and this is really different stuff. And so it's very interesting. It feels very odd because it's not what you're used to. That's okay. It's okay to feel a little odd with some things we do sometimes. So let me just take a look with you at some information about how the polar coordinate system works. So this is a system using coordinates based on distance from the origin and that distance is referred to as R. Oh, that's funny, as R. And the angle measure from the positive x-axis. Referred to as theta. So an ordered pair here looks like r theta. So the distance followed by an angle measure. All right, so visibly, or visually, I should say, if you're talking about this particular point, just randomly out there in the middle of whatever, it has a distance to the origin. That's the r we're talking about. And if you were to draw a like a line going through the origin, there would be an angle measure theta associated with its location as well. Okay. If we restrict our r values to being positive, and we restrict our angle measures to being between 0 and 365 degrees, we have a unique representation for that. Okay? But we're not restricted to those things in general. All right? So, for example, if this is a distance of, say, 2 away, and the angle measure that I chose right here is pi over 3, there are other ordered pairs that would put me in that same location. And here's an example of one. I'm totally making this up on the spot, so we'll see if I can get the angle measure right. Okay? If I go in the other direction to here, I could still be 2 away, and that would be called negative 2, because I'm going the wrong direction. And the angle measure could be done going this, if I go, what do I want to do? All the way from, hang on, I didn't set that up right. This is what happens when you just decide you're going to do something and you haven't actually practiced it. I don't advise it, okay? All right, so let me try again. If you go the radius of 2 and you go an angle measure of 180 plus this, basically pi over, so if we did negative 2 and then we did 4 pi over 3, that would do it. So 4 pi over 3, I'll do the angle measure first. 4 pi over 3 would put me down here where I was at, and then the negative 2 would actually make me go the opposite direction. Instead of coming out to the side this way, I would go backwards. Okay? So just to give you some perspective, we actually have multiple representations for every one of our points. And if we don't, have the angle measure going between 0 and 365, or 0 and 2 pi, if you go 2 pi around again, you're in the same location, right? Think trig. You know what I'm talking about, right? This is very triggy related. A few measurement or a few conversion notices. There's a relationship between our rectangular coordinates that we've had before and this new polar coordinate. One of them you can see really easily, except that I've got a mess on my screen, so let me delete a few of these things. This point right here, if I were to create a triangle here, do you see the Pythagorean theorem coming into play? This is my distance x, this is my distance y, so there's clearly a relationship that says that x squared plus y squared equals r squared. So that's one relationship piece. Another relationship piece is that, from trig, is that angle measure, theta, in the middle there, the tangent of that theta is equal to y over x. Right? Tangent of theta is opposite over adjacent. The opposite is y, the adjacent is x. So that relates the angle measure back to x and y. And then with a little bit of trig and manipulation, you'll get the other two pieces that we can use frequently, is that x is r cosine theta and y is r sine theta. So with these four pieces of conversion ability or material or whatever, we're able to move back and forth between rectangular and polar coordinates. Okay? We can do it both in terms of specific ordered pairs, and we can do it in terms of equations, and that's what we're going to do next. Okay, does everybody have everything that I have so far written down? Okay to switch screens? Okay. Well, that's when you were supposed to say no beforehand. A little faster, Ethan, a little faster. It's all right.
Thank you.
You're welcome. Okay, so let's do an example with just an ordered pair. Whoops, still had that box going on. We're going to plot the polar coordinate. R theta, and find its rectangular representation. I'm going to say rectangular form because it's quicker. Okay, rectangular form. And the one that we're going to do is -3 pi over 2. And I mentioned this before about the negatives, and now we have one that's actually going to be plotted with it. So here's my axes. You can start with the -3 if you want. It's on the left if you'd like. Or you can start with the +3. If you start with the positive, or you could start with the 3 pi over 2 is what I meant to say. If we were doing +3, we would move 3 to the right along the x-axis, and then we would rotate. Does that make sense? We're starting with -3, so we're going to start -3 on the x-axis. The distance is 3 in the negative direction. And then from this location, we're going to rotate 3 pi over 2. Where will that put me? Yeah, Shayna's right. She's throwing it up in the air for me. It'll put me all the way around like this. Yep, that's a 3 pi over 2 rotation. Everybody good with that? Okay, that's not measuring from the positive x-axis. It's measuring from the -3 location. You with me? So this ordered pair is actually right. Let me shift this just a tiny bit because it's in my way. Right here at 1, 2, 3. Chances are pretty good that you know what that ordered pair is in rectangular form without really converting anything, just simply because it's easy to see. So what is the rectangular coordinate here? It's 0, 3, right? Okay, everybody good with that? We'll have plenty of time practicing with the others on the other ones. If you wanted to start with the 3 pi over 2, just for good measure, if you wanted to start with the angle description. If you went 3 pi over 2 to start with, you would be here, right? You'd be on the lower y-axis. And then if you go -3, instead of being on the lower y-axis, you would go in the opposite direction, which would put you on the upper y-axis, and then you'd be in the same spot. Okay, so that's another way of thinking about that. All right, let's try another one where we're not asked to plot it, and it will be sort of from the same perspective that we were looking at the last one. We're going to find rectangular coordinates for the ordered pair 2 pi over 4. We'll graph it when we're done just so that you can sort of visually verify that it makes sense to you. 2 pi over 4. All right, so we have over here some equations that tell us how x and y are related to r and theta, right? Those last two in particular are quite helpful at the moment. X is equal to r cosine theta and y is equal to r sine theta. So if I use those pieces of information, I can find what I'm looking for here. X is equal to r cosine theta, r is 2, and theta is pi over 4. So what is the cosine of pi over 4? You remember? Square root 2 over 2 times the 2, you betcha. So this is actually just square root of 2. That's x. How about y? Y is r sine of theta. So I have 2 sine of pi over 4. What is the sine of pi over 4? Yep, square root 2 over 2 again. So I have another square root 2. So my rectangular form is root 2 over 2. I'm sorry, square root 2, square root 2. And if we think about this from a graphical standpoint, not because we have to, but just so that you can see that it makes sense, if you went out 2, and then you swung around pi over 4, right, you'd be somewhere about right here. Agreed? And not only that, but the distance here and the distance here would be the same, and they're both 2. And using the Pythagorean theorem, you very quickly would have still arrived at the square root of 2. Okay? Everybody good with that? Oh, I've got it written wrong. Huh? I'm sorry. I put my 2 in the wrong spot. My bad. I just put the 2 in the wrong spot. Let me fix it. I started this 2 out here. This one's 2. There we go. Thank you.
Yes.
That's what it is. I was like, that doesn't look right. It started out at, and I didn't. Okay, let me actually fix my picture. You know what? If I go backwards, it'll work. Make it bigger. So when I swing it around, it'll be at about like right here. Bigger, better. This is my 2. And then, if you can see this piece now, there we go. So these pieces, x, are the same. And so then if you were to do Pythagorean theorem, x squared plus x squared equals 2, you'd find that x is equal to square root 2. So there we go. At any rate, so that's how we can find either from a visual perspective, if it was the earlier one, or this one that I looked at graphically there at the end, or from an equation kind of standpoint. We're going to go the other direction now. We're going to start with rectangular coordinates and find the polar coordinates to match, okay? So we're going to find 2 sets of polar representations of the given rectangular point, and our point is 3, 4. So of the point 3, 4. All right, so how can I find r or theta when I'm given x and y? R is 5. How do you know r is 5, Kyle? Right, x squared plus y squared equals r squared. I have 3 and 4, and that's one of our wonderful Pythagorean triples, right? So r is 5. Does it have to be 5? It could be -5 as well. So just for the sake of, we know we're gonna have to create 2 equations here in a minute, right? Or two ordered pairs. So we might as well create one of them here. Make sense? I'm gonna have 2 representations for r. Tangent of theta equals y over x, so that's 4 over 3. Okay, and I don't know what your book will tell you in terms of measurements. Let's do, I know radians, but I mean in terms of decimals. Let's go with 2 for now. Will that work? 0.93, fantastic. So my theta, approximately 0.93. So one of my ordered pairs is actually going to be well, in fact, we can actually make sure that we're getting the angle right. So the angle and the ordered pair matching up right. So if we're looking at our coordinates and we're at 3, 4, we're in quadrant 1, right? So if I have the angle or the R value of 5.93 makes sense. Is everybody with me? A radian measure of almost 1, right? Because the radian when we get to the positive y-axis is pi over 2, which is about 1.5. Are you with me? Pi over 2 is about 1.5. So between 0 and 1.5, radian measures would be in quadrant 1. So this is one of my ordered pairs. One of my ordered pairs would be 5 and 0.93. What would I have to do to find another one? Obviously, -5 is an option, but what would I do to get the angle then? Yes, so
No,
if...
Don't you just add 1 pi?
I'm just saying that.
Don't add 2 pi. 2 pi is 360.
Yeah, that's what you want.
Okay, so that's another way to do it, Deborah. There's 2 different things. So hold on to that thought for just a second, because we're going to do that one too, just so everybody sees it. Ethan, tell me what you had thought about the pi.
I was thinking of just pi and then -5.
Okay, so if we make it -5, we're actually it's like going around 180 degrees, right? Because we've gone the opposite direction. And then you can add pi to that. So I'll put 0.93 plus pi here. What's that?
You add 2 pi, does it have the same?
Yes, that would be another way to do it, unless your problem restricts you to like between 0 and 360 or 0 and 2 pi or something like that. So this would be a second option.
But if you do 2 pi, it would be 5, not -5.
Yep.
Could you also subtract pi?
Yes, you could. So you could do like -5 and 0.93 minus pi.
I can't eat all this pi.
Can't eat all this pi. You only have to find 2, right? Yeah. So we found 4 because we're overachievers. You guys are awesome like that. Does everybody have a sense of how that works, though? All right. So if you change the angle, if you change the distance, the R value to make it negative, you're adding a pi. And otherwise, you're adding 2 pi if you want to keep the R value the same, or subtracting pi or subtracting 2 pi. Yeah. Okay, cool. All right, let's take a look at a couple other things. All right, this is the one that I have next for us to do. This is number 4. We're going to use a graphing utility because that's fun, right? To graph the polar equation. I haven't even given you a polar equation to know what those kind of look like. And we're going to find an interval.
Polar.
Did you find polar in there?
Yep.
Good.
Yeah.
Find an interval over which the graph is traced only once. I'm going to show you how you know that. Here's the one we're going to do. We're going to do R equals 2 minus 2 cosine theta. No, we need it. Well, is your polar set up?
Yeah.
Okay. So let's see. Did everybody find polar mode? If you click on mode, yep, the 4th line down, you've got function, parametric, polar. We did function and parametric, so now we're doing polar. And if you hit y equals, you'll see now that they say R1 equals, R2 equals. Is everybody at the point where they've got R equals on your screens? Shayna, are you good? Okay. You just had a confused expression for a moment, so I want to make sure it looked right. Yeah. Andrew, are you guys good back in the back here? Y'all good
Is this
too?
supposed to be a small window?
We'll get the window fixed in a second. So did you do 2 minus 2 cosine theta? Okay. Theta turned into, x turned into theta, didn't it, when you clicked on it? Yeah, good. Okay. Let me get this screen switched over. All right. And I told you we were going to kind of play with this together and see if we can get our screens to cooperate. All right, so think with me about what you know about cosine values. What kinds of values come out of cosine? -1 to 1. All right, and we're multiplying that by 2. So now we're doing -2 and 2. And we're subtracting that from 2. So we're looking at values that are small. I guess that's my first point, is that the values are small, because I think somebody said, does it look really small? Yeah, it's going to look really small with this particular equation. My window is what I wanted to look at. So my window is still maximum xy. I mean, like I've got an xy window. I still have to tell it that. I'll come back to the thetas and everything in a minute here. So my minimum and the maximum, maybe like -4 to 4, -2 to 2, something like that's probably appropriate. I'm going to just put mine at 4s just in case.
I have mine set at the standard and it converted mine.
Did it? Cool. We don't really have any reference points for theta yet, correct? We really don't know what we want theta to be, so I'm just going to leave mine. Right now, mine's going from 0 to 2 pi. Is that what your default was? Anybody else's?
Yeah, it's 360. But
360. Yours is set up in radians or degrees?
it's in the core. I can just
Okay, change it to radians.
If
Change
you
it to
only
radians.
wanted to get this graph once, traced once, what would you want?
It's a good question. And the answer is it depends on the equation you're working with. It usually depends on whether or not you've got double or triple angles inside of your cosine. So if we have cosine of theta, 0 to 2 pi seems reasonable. But if we actually had like cosine of 4 theta, we would not need a full 2 theta or 2 pi around to get the whole circle or the whole graph to go. All right, so I don't know what this looks like. Let's see. Oh, look, it's like a heart, kind of. Do you guys see the divot in here? Does everybody just have that divot? The different shapes created have different names. I'll let you reference. There's a list in your book of the different shapes. Some of them will actually give you little like little loops on the inside here when they do it. Depending on if you do double and triple and quadruple angles and things like that, on the inside you'll get petals. They look like flowers. You get some cool stuff. So let me just see what happens. I want to change this equation just to say 2 theta to see if you guys can see what happens. What I want you to watch on your screen when you make it say 2 theta is I want you to watch it graph and watch the little bar, the little status bar, because that actually tells you when it's done graphing. You know what I'm talking about, right? Watch your status bar when you put in 2 theta. Oh, I got 2 circles. It's not what I was expecting. Let me try 4. Look, fun stuff. I wanted to show you all sorts of great things. This is great. Now I've got a petal.
I'm assuming it's just going to keep increasing the number of petals.
It's a good question. Let's see what happens with 5.
Well, it's
There's
5
5.
petals.
It's 5 petals. Oops.
Dr. Hans, what happens if you do 1/2 theta?
Oh, that's a good question. Look, there's my 6 petals. Let's see. You want to do 1/2 theta? No, I don't know. Let's see what happens.
The heart shape is a cardioid.
Thank you. I wanted to say cardioid, but I didn't want it to be wrong. Ooh.
Oh.
What happened, David?
Someone broke his heart.
It made a spiral. Somebody broke it. It made a spiral when we had 1/2 theta. Woo. Oh my goodness. Okay, cool stuff. All right, let's fix it back to what we were supposed to have, which was just theta. So here's our cardioid. Thank you. I didn't remember what the names were because I wasn't looking for that with the parts I was teaching
If
today.
you go to 4 pi with the, what? If you go to 4 pi with the 1/2, you go to the loop inside
So with the 1/2, you said?
Yeah, so if you go to 4 pi.
There's the rest of my loop. That's actually what I wanted was my loop. There you go. Isn't that a cute one? There we go. All right, let's put it back at our theta. That's what I actually wanted to show you. So that actually, okay. Take your window just for fun right now. Just make your window say 2, did you say 2 pi? Make your window go from 0 to 2 pi on your theta max in your regular graph that we're supposed to be doing here, 2 minus 2 cosine theta, and watch your status bar. Well, you're going to have to manipulate something. 4 pi.
Okay.
Double it is what I meant to do, and we were already at 2 pi, yeah. If you look at your status bar, the whole image is already drawn, but the scrolling continues. Did you see it? Okay, so that actually told us that we went too far. We didn't need that whole theta that we did. So if I were doing it at, let's say, pi, we have that sort of almost a half a spiral like we saw before, right, David? And we get the feeling that it's somehow incomplete. There's something missing. And so we need more of an angle measure. So in fact, I need 2 pi to make this one work. And that would be the other part of the question that I was being asked.
4 pi, it's just tracing over it again.
Yes, it is. It's exactly right. And if you look back at the directions on this one, it says the graph is traced only once. So we're going to actually write down an interval here, and that will include our 0 to 2 pi.
Will that interval always be 0 to 2 pi?
No, it won't. The one that David had just looked at when we had 1/2 pi for a moment over there, it had an interval that would have been 0 to 4 pi. Yeah. So, all right, let's take a look then and write this down. I didn't draw it while I had it up, but you guys still have yours up. It looked something like this, roughly speaking, right? It's a sketch. And our theta went from 0 to 2 pi. All right, we're going to do another one, different equation. Slightly different directions, not substantially, but slightly. We're going to sketch the graph. So that's going to be with the calculator if you'd like. And the graph of the polar equation. I think I isolated my questions. I was thinking I was going to ask you to change it to, well, you know what, we will. Why not? And find a corresponding rectangular equation. I have it in the notes anyway. And our equation is actually going to be r equals 2 sine theta. So go ahead and take your calculator, type in 2 sine theta. And what does your image look like? I don't want to put my other screen up if you don't mind. It looks like an ellipse. It actually isn't, but do you know why? Somebody said circle. How do you know it's a circle?
It looks even based on.
Is it because of the warping effect?
It is. Your screen is a rectangular screen. You all know what I'm talking about, right? Like how it's longer than it is tall. Click on Zoom Square, which is Zoom 5, and it will square up your window to put it actually under the Zoom button, Zoom 5, and it will make your window actually square. So like, you know, your X distances are exactly the same as your Y distances. And do you see now that it really is a circle on top? It was hard to see. It is still an ellipse too. Yes, I know, but it's a circle-shaped ellipse. How's that?
It looks like somebody dented mine.
Somebody dented yours?
Yeah.
All right. That's what I've got. Yeah. It's because of the T-step. If you make your T-step smaller, Ethan, it will make it smoother. Yeah. In this case, it's not T-step, it's theta step, but yeah.
I made it 0.001.
Does it look nice and smooth now, Kyle? It's taking forever. that might not be your best choice.
Whoops.
Yeah, it's a lot better. I think we.
Okay, glad to see that it looks better. Wonderful. Okay, let's go ahead and find the corresponding rectangular equation. Y'all ready? Okay. This looks a little bit funny because I don't have, any of the specific. I mean, like I could change the R on the left to say, well, and I will. But I don't have an R. What was it? 2 sine theta. The equations back over here don't say R equals, right? And they don't say sine of theta equals. But could we manipulate them so that they did? We absolutely can. Let's start with the sine theta part. If I were to take this equation at the bottom and I were to solve it for sine of theta, what would that look like? Sine of theta equals y over r. Everybody good at that? And of course, we could do the same thing if cosine showed up on some problem, right? I want to replace sine of theta with y over r. Do you see something amazing about to happen?
R squared.
I'm going to get an r squared. Yes, I am. R squared equals 2y. I want a 2y, so I'm good with 2y being in there. And then r squared is the same thing as, and then technically speaking, we're done with finding a rectangular equation. It's not very identifiable per se in this form. You probably can tell it's a circle, but you can't look at this to tell me right now where it's centered or what its radius is in this particular form. So depending on what the questions ask next, you would put it into a form that's recognizable because that's going to be usable for us. So if I move the 2y to the other side and I complete the square. So how will the negative 2y complete the square? What do I need to add? Close. It's 1. Yeah, it's 1. So let's see, I have y minus 1 squared equals 1. Are you guys good with that? Okay. Does that look like your equation? Do you have, I've drawn it on my screen. Is it a circle? Is it a circle with radius 1? Yeah. Is it centered at 0, 1? Yeah. Those details match the picture that you've already gotten. However, it is very interesting that in rectangular coordinates, you don't have a way to enter that in your calculator, do you? No. No, not very conveniently. It would be a mess to try to solve for y, right? Yeah, super ugly. Okay. Could we have figured the equation out from the graph?
Yes.
Yes, on this one you could have.
But do you have to solve it like this, or can you just say by the graph?
So
It's centered at 0, 1, and the radius.
It would be better that you practice this.
we're going to practice this because some of it, they're not going to be obvious. They're not always going to be clearly obvious. Oh, look, the center is at 0, 1. Oh, look, the radius is 1. So for the sake of just consistency and practice to a point when we absolutely need it that way, we'll go ahead and solve it out with some equations, okay? Good questions, Becca. All right, let's try another conversion. We're not going to draw on this next one, so if you weren't drawing, you wouldn't be able to do it either, I guess. You could still graph it, I suppose, but we're not asked to on this one. We're going to convert the rectangular equation to polar form. And I guess I lied to you. It says and graph. I just wasn't looking clearly. Here's our rectangular equation. So before we go converting anything, do you know what this is an equation of? It's a hyperbola. Good job. Is it a hyperbola opening up and down or left and right? It's up and down, yeah. When the y squared's first, it's up and down. It's been a couple of days. Yeah, it's been a couple of days. It's all right. So this is a hyperbola. As we're looking at working through this, we should be able to, in fact, let's do that first. Let's take the graph of the hyperbola as we would expect it to look, and we'll check it with our graph in polar form when we're done, okay? So if we were to convert this to standard form for a hyperbola, I would simply divide both sides by 4, right? It would look like this. And in my graph, I would actually, because it's 2 squared underneath each of them, I would go out 2 in each direction to get my asymptotes. It's centered at 0, 0. I guess I should say that, even if I didn't, I meant to. These points right here will give me the asymptotes that I'm going to draw in. And then my vertex is actually, vertices are at positive and negative 2 on the y-axis. And it looks something like this. Is that good for everybody? Okay, let's go over to the converting part. So what is y? Go back to your list. What is y? R sine theta. So I can write in here r sine of theta squared. What is x? R cosine of theta squared, and it equals 4. So technically speaking, that's going to be the polar form, but we're going to clean it up because that's a mess. So now I have r squared sine squared of theta minus r squared cosine squared of theta. It equals 4. Notice they both have r squared in them, right? If I were to factor out an r squared, I would have sine squared theta minus cosine squared theta. And I'm going to post out on I almost said Jupyter, that wasn't even it at all. Moodle would have been before. Now we're doing Canvas, whatever. I'm going to post in Canvas some trig identities to help remind you. That's a trig identity, not one we use as frequently as the Pythagorean theorem, but it is a trig identity. It's actually the cosine of 2 theta. Okay? So I'm not asking you to go back and memorize trig identities. You should know the most basic ones, but these other ones like double and half angle, I will give you if you need them, okay? So anyway, at this point, if I were then to try to solve, I would actually be able to write this or try to plug it in your calculator as r squared equals, it's actually, I should have put that in there, a negative cosine of 2 theta. So this is r squared equals 4, or negative 4 over cosine 2 theta. Okay, you can square root, yeah. So r would equal, if you wanted to graph it, like this is a perfectly cleaned up, acceptable way of writing it. There's nothing wrong with that. But if you wanted to graph it, yeah, it would be equal to plus or minus of 4, negative 4 over cosine of 2 theta. And you'd have to be careful that you actually end up getting only the positive parts underneath there that make sense and so forth. And you could confirm that then with
It only works
the calculator.
when you take the angle and it becomes negative.
Yeah, and it gives you cosine values that are negative. So it's very, very specific, right? Cosine values are only going to be negative from pi over 2. Well, specifically, the angle inside would need to be from pi over 2 to 3 pi over 2, but then it's doubled inside, right? So it would be from pi to 3 pi. It's doubled inside, so half of that, pi over 4 to pi over 2, to make that work.
So for it to be a good polar equation, it has to be set equal to r.
Yeah, you want it to say r or r squared is fine. You can write it as r squared equals. There's nothing wrong with that. Yeah. Yeah. Any questions on that?
Is that it?
That's it. I have some homework for you. This is kind of like the last time where the written part's kind of long. The web assign's fairly short, so try to balance that a little bit. This is page 722. 5, 8, 11, 18, 27, 30, 37, 40, 43, 46, 78. Some of them are graph on the calculator, right? 83 and 86.